Check this works. That doesn't. Cool. So yeah, I'm Michael, and I'm going to be talking to you today about, is your code fast enough? Assuming everything works. Cool. So why should you even care about is your code fast enough? Well, the simplest answer is that there's actually several bodies which have limits on how long your models can take to run. Like they have to be run within a working day, or you have to agree a time with them. And so generally speaking, there is some limit that you have to approach. However, a lot of the time, it's nothing to do with them. It's actually to do with your model itself. You may have a minimum fidelity threshold. Your statistical space may just be so large that actually you need to run a lot of samples to actually be able to interrogate it properly. You may have a non-linear scaling model, which often means it might be really fast at low numbers of people that say patients that you're modeling. But if you're doing a lot of patients, it suddenly becomes incredibly intangible and not really possible to explore. And then there's things like value of information, which are generally incredibly computationally heavy, and imputation, which can also be incredibly computationally heavy. But you may be as simple as a technical constraint. I'm privileged. I get to work on Isambard. This is a computer with something silly like 100,000 cores. Most people work on a laptop. That on a day like this, I don't think even one core will work. And if you think, it's okay, I can buy a better laptop. This is the price of RAM. It has quadrupled in price practically. You will not want to buy a new laptop anytime soon. And then there's some more sort of impacts, which are things like the environment. There is a cost to every kind of modeling that we do. You may be doing a technology demonstration. So you may be explicitly saying, I want this to be as fast as possible. And think about this from a different perspective. It's not about speed, it's about efficiency. If your laptop is sat there for 8 hours just crunching something and you can't use your laptop, it's costing you money. And so we first got to ask the question, well, how do we even know how fast our code is? Now, the traditional process that most people will use is benchmarking. So on the left-hand side, it's this incredibly small flowchart. And it's basically, you time your program. Is it fast enough? If not, do something to make it faster, try again. Now, this is what almost everybody starts off with, except it's not very good. Instead, you want to use something that's called profiling. So profiling is typically done using an external profiler, but the principles behind it can actually be done just with manual entries of timestamps within your code. And profiling is you run your profiler, you ask the question, is my code fast enough? If it's not, you now have a list of profiled functions. And these functions contain things like, how fast did it run? How many times did it run? Things like that, which now allows you to pick a specific time-consuming component of your code. And then you can ask the question, can that specific component be optimized? Now, unfortunately, sometimes the answer is no. For example, input-output, it's about as fast as it's ever going to get. Whereas if instead we can optimize it, you will have to then start right at the beginning. Because once you have changed something, and this is the biggest mistake most people make, they don't bother timing again. They assume that because they've made something that is theoretically faster, it is. I cannot tell you how many times I have done the theoretically faster method and gone 10 times slower. So always time after every change. And so there are a handful of tools that you can use for profiling. I've thrown up a selection of them here in R, Python, and C++. I have not used all of them. I have used at least one in each of these. And this is not an exhaustive list. There are probably nearly 100 profilers, and the Wikipedia page for it is full of ones that work on multiple languages as well. So, what does a profiler actually give you? Well, it gives you something that's incredibly hard to understand and read, unfortunately. All of these, if you look, are approximately the same in output. But the gist of it is, it tells you how often it does the profiling. So in this case, 0.01 seconds. It tells you how long this top function ran as a percentage of the total runtime, absolute time, how many times it was called, the milliseconds per call. Yeah, we're getting really small units now. And then what the name of the function actually is. So in this case, the test code called the open function 7,208 times. That means this function needs to be incredibly fast for the total runtime to only be 0.02 seconds. And you get similar things in Python. Unfortunately, with Python, you'll get a lot of these built-in method calls. This is just saying you're calling another library. Sometimes you can tell the profiler how that works. It might require a little more teasing out, but often it doesn't really matter. And then in R, once again, similar process, just some of the columns have been reversed. Now, I don't know about you, this is unintelligible. I can understand this because I've been doing this for 10 years. I much prefer this. You can take almost all of those outputs and you can pass it into something called gprof to dot. It is because someone was incredibly fed up with not being able to read these things, and instead, you get a dot graph. And the beauty of this is it's sort of like a dependency graph. It's not quite a dependency graph, but it's sort of a dependency graph, where you can see, oh, actually, I don't really spend any time in any of these because they're only called 0% of the time. So once. But if you look in this bottom left-hand corner, you can see I'm calling this, I think that's 1 billion times plus. And that makes up 41% of my runtime. And then the other one is the same number, but that one is only 37% of the runtime, which means this force calculation is apparently faster than this potential calculation. But if I'm going to improve my code anywhere, I'm not going to be sat there going, yes, the S2R8 function, this is definitely the one that I need to improve. I'm going to be sat here basically always looking in this bottom corner. And these graphs can become ginormous, okay? But incredibly useful for picking out what it is you actually need to focus on to accelerate your code. Now, here is an example. I did some work for ARM. They had a bug in their code. I did a benchmark. The blue line should be where all the other lines are. The issue, now this is using the ARM profiler, so just another choice. Wherever it's light green, that means it's multi-threaded. This is almost all light green. This was using one fast Fourier transform library. This was using ARM's fast Fourier transform library. It's all dark green, which means it's all running single-threaded. And so just visually, you can immediately go, oh, well, I now know the issue. I thought it was doing this, it's actually doing this, and it gives you some more information about where you actually need to look to understand what the problem is. Now, what I haven't shown you here is those lines of text, which also tell you exactly where the problem is. But there is a problem with what I'm telling you here. I'm telling you, you need to optimize. There is lots of famous quotes by this gentleman, who is functionally the architect of programming. And all of them come down to, don't optimize too early. And this trope exists for a reason, okay? You can find so many comic strips on this. The trope exists because you can spend hours, days, months, years trying to optimize something to use it, and then realize you've actually picked the wrong method, or you don't ever actually get your product out the door, or you run out of money. You know, there is an unfortunate subset of people who think it can only go out perfect, but don't let perfect be the enemy of good. However, program design does matter. As this flowchart says, if you have to ask a flowchart, you're optimizing too early. If you're not asking the flowchart, then it's time to make sure your program design is correct. So these are basically preemptive optimizations. It's things you should just do by default, regardless of what you are doing. And some of these are simple as check your algorithm. I was working with a colleague who was doing something in n cubed time. There was someone else who had discovered you could do it in n time, and then he wondered why his code was running incredibly slow. Choose the correct language. Now, I appreciate this is R for HTA, but we have seen here that VBA doesn't have to be the worst thing ever. You could also use Python. You could use R, C++. Depending on what you are doing, you may choose to go higher or lower, and it will affect how fast your program will run. But then you've got the more actual nitty-gritty stuff. Follow the program memory order. R is a column major program. C is a row major program. Fortran, column, Python, don't go there. This sounds like something that's not really worth thinking about, but I will show you a couple of examples where it matters. Minimize your input-output operations. If you're writing one file every second, 95% of that time is going to be the writing of the file. If you can write all your files right to the end once, then it will be incredibly quick. And then avoid conditionals and loops. If you have to put an if statement in a loop, there is a couple of design considerations you have to do, but if you can never put an if statement in a loop, that is the optimal solution. Here's a picture of my cat. I thought it was needed on such a heavy topic, but she is a princess. So, how do you make this faster? You're always stuck on this bit, and when you look into it, it's actually incredibly complicated. You've got all of these potential paths you can take. Some of them cross over. What I haven't shown here is some of them lead backwards. And it's sort of this amorphous mess of potential optimizations that you can do. So the first place you can start off is understanding your hardware. And there was a question earlier that sort of highlights this. You have memory on your CPU. This is the fastest memory. It is so incredibly fast, often you don't even know your computer is finished doing the job after you've pressed go. You've then got RAM, then SSDs that go in your NVMe slot, then SSDs that go in your SATA slot, spinning Rust, the internet. Anything on this side you should avoid at all costs if you're using it for data access. Storage, absolutely fine, no issues. But as soon as you're working on the data, you want to be here or on there. Now, that sounds like a really weird thing to say, but if you're working with data that is incredibly large data sets, often you end up doing swap spaces on your SSDs. Ask for a computer with more RAM. It will probably half or even quarter the amount of time just by having more RAM. Not a faster processor, just the RAM. And then there's the other memory consideration. This diagram explains row versus column major quite nicely. It's literally just, how do I store my matrix in memory? The matrix is on the left. How it's stored in memory is on the right. You can see that as you would step across this, if I wanted to go across the row here, it's nice and easy. Across the row here requires me to jump multiple spaces, and this causes an incredible penalty in your ability to work. And this code here actually works if you wish to try it. And this shows the difference. Okay, it's a bit of a silly example. It doesn't do anything interesting, but this is in C++. So in C++, this causes a humongous issue. And then you've got the I/O operations. As I sort of said, you're going from RAM, which is already not as fast as your processor, to the SSD, which is slower again. And this is what it looks like if I decided to just write a number out once versus writing it out all the time. It's an incredible difference. I'm writing the same number of numbers, but it's a ginormous difference. And so these are things people make mistakes of, not intentionally. You don't go out there to go, yes, I'm going to write as many files as I can. It's just you've designed your program in a way and it's locked you in and suddenly you're here. Now this is an interesting one, breaking the pipeline. Computers can sort of be thought of like a pipe, in that you can feed a lot more water in than stuff you are taking out. So you might only be pulling out one instruction at a time, but you can have 15 instructions halfway performed, okay? But if you put an if statement in this, everything that sits in this block here has to be thrown away if the if statement is incorrectly predicted. So this is what the branch prediction part is. So if I have random data, and once again, you can use this, you can explicitly pull this example out. Random data of, I don't know, it's like 1 billion samples or something. If I sort it first, it runs in about half the time. But not only does it run in half time, look at the error bars. It might run marginally slower, or it could be almost a quarter slower again, versus your unsorted, where it's not. The reason for this is because your computer is effectively trying to guess which way you're going to go. So try and help it, because if you can help it, it runs faster. And here is an industry example of this. This is once again from ARM. I literally just swapped the order of if statements. It was as simple as that. They had combined 2 if statements into a single block. I pulled them out into 2 blocks and swapped the order. And splitting the 2 blocks alone saved a small amount, but swapping the order was actually the important part. So ordering your if statements in your loops are incredibly important. And so this shows on the left-hand side, shows how much faster this actually made the program, which is to say an order of magnitude, just from swapping the order of if statements. And then you've got multi-threading. Basically, you can only accelerate a program to the speed of the slowest single-threaded section, which is a bit of an oversimplification, because you can also do this, where actually, as you throw more threads at it, it gets slower. Now, this is often due to overheads. It's when you're trying to do something single-threaded or not very well multi-threaded, but you keep throwing calls at it. And all you're doing is spinning up more and more usage without doing anything. But you can accelerate this. So here, this is why, and this is where profiling comes back in. Hey, it comes back. On the left-hand side, I profiled my code. Now, I profiled this not using a profiler. I literally just put timestamps in my code and just printed the timestamps out. I've got this lovely straight line. This is like the perfect parallelization. Couldn't get it better if I tried. And then you've got these red and blue ones, which are absolutely atrocious. Well, as it turned out, there were ways of making these better. On the red line, I could definitely accelerate that. I knew I could from the beginning. The blue line, though, if you notice, even though I have done a reasonably good job, it's still tapering off at the end. And this is sort of that Amdahl's law kicking in. This is where there is something in here where it doesn't matter how many calls I throw at it, it has almost a static runtime. And this will eventually be the cap on how fast my program can go. So this is something you've got to consider when you're throwing more calls at things. And then this is my final lovely slide, which is, I didn't realize was going to be so pertinent to today, thermal throttling. Modern computers are incredibly smart, and that is to say they don't kill themselves when they get too hot. However, to do that, they slow down. Now, on your average desktop computer, not an issue. You've got a big fan and a heatsink. Your laptop? Yeah, it runs half as slow. Half as fast, sorry. So this was, once again, some data I took at ARM, where just repeatedly running the same program over and over, back to back, and you can see how I'm heating up the CPU, and eventually it stagnates at a speed. Now, this wasn't meant to be an exhaustive lecture on all the ways you can do this right and wrong. I'm hoping that I've given you like a nice breather, refresher, whatever you want to call it, where you look at this and you go, that's something to think about. And now, unfortunately, I do have to say, you also have to think about my acknowledgements, which is lots of people over the last 10 years. So there are some things on here which I actually had to look up from my thesis around. And then I sort of have this statement. I actually have a really big passion for this. I love making software go fast. It's actually probably what I enjoy more than anything else. But I don't expect you guys to have that. But what I do hope you to have is questions. And so if you have questions now, if you have questions later, if you have questions tomorrow, please do ask them. Thank you.
Do we have some questions now? Any questions. Oh, yeah. I'm going to get my steps in now today.
Thanks, Michael. That was a really good presentation. I know I've struggled with this, and I'll take a few learnings from this and go try to apply to my code. I have a question about using Profiler with things like R6 objects. I haven't succeeded in getting into an R6 object with a profiler. It can break down a function, but I don't know if you have any experience with it.
I've not explicitly tried. I'm sorry. Thank you. So I've not explicitly tried with R6 objects, but object-oriented programming languages have had profilers for a very long time. So it may just be that you need to change which profiler you are using. So Python, for example, is another OOP language, and their profilers get inside absolutely fine. C++ also has profilers that happily get inside objects. So there is probably a flag you have to set for your profiler for it to do that. That's a common occurrence. Unfortunately, a lot of profilers require some level of command line expertise. So I would suggest the documentation on that one.
Any other questions? I don't think there was any online. Oh, yeah, there's one more here.
Cheers. Yeah, that was a really enjoyable presentation. I might just be being really stupid, but I don't understand why sorting beforehand helps. I wonder if you could explain that a bit further for me, because I'm just not getting it.
I was about to draw on the whiteboard, but there's no pens. So if you think about getting a series of random numbers between 0 and 1, say 100 long, I ask you to put them in two piles where one of them is below 0.5, the other is above 0.5. If I give them to you as a string of random numbers, you are going to have to check every single number every time. If you sort it, you've still got to check. But what you can do is you can go, oh, well, I know that the first 5 are probably all below 0.5. So you assume they are, and then you sort of check all of them at the same time. Much cheaper. Because and now if you sort of extrapolate that to programming, it might be you're doing a function that has some very complicated mathematical output, but the mathematical output is actually, you can understand if it's going to satisfy or not satisfy your function in a pattern. Now, modern computers can actually detect patterns. So if you have patented work, it can still do it even if it's flitting backwards and forwards. But if you have like truly random data, it's awful. If you are using an older computer where it can't even detect patterns, and there are patterns and there are patterns, going yes, no, is an easy pattern. Having some other pattern that's like a symphony or something, yeah, that's going to be much harder for the computer to follow. So yeah, you're basically just helping it guess, for lack of a better word.
Thank you very much. I think any other questions, just for time, we'll maybe put on the chat and you can respond. But thank you very much, Michael. Yeah, thank you.